Okay, now we're going to use a tool called dimensional analysis, or actually a process to actually solve some unit conversion problems. And we can use it to solve everyday problems and then problems for us in chemistry also. So here, dimensional analysis, it says, is a way to analyze and solve problems using the units or dimensions of the measurements. So if you want to take a second to get this definition down, you may see it again. A way to analyze and solve problems using the units or dimensions of the measurements. And again, we can use this to solve everyday problems, or as we get further into the course, you're going to see how we use it many times in a process called stoichiometry, which is in the second half of the course. We'll use it extensively. Okay, so for our first problem here, using dimensional analysis, how many seconds are in a workday that lasts exactly 8 hours? So if we work 8 hours a day, how many seconds does that come out to be? So we, number one, analyze the knowns and the unknowns. This textbook wants you to go through a process of looking at everything that you know and then try to figure out everything that you're searching for. So it says to convert time in hours to time in seconds, you have to use two different conversion factors. One is to convert from hours to minutes and then minutes to seconds. So first you convert hours to minutes and then minutes to seconds. Identify the proper conversion factors based on the relationships. 1 hour equals 60 minutes and 1 minute is equal to 60 seconds. So 8 hours and seconds worked, that's what you know and what's unknown. And then below here they have the two conversion factors that you're going to use. 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. That's everything that we know, and what we want to know is in an 8 hour time period, how many seconds? That's the unknown. Okay, so the first conversion factor is based on the fact that 1 hour is equal to 60 minutes. The unit hours must be in the denominator so that the known unit will cancel out. Because we're beginning, we know that the original time was expressed in hours. So 1 hour has to be in the denominator so that it will cancel out. And you'll see on the next slide or two what that means. The second conversion factor is based on the fact that 1 minute is equal to 60 seconds. The unit minutes must be in the denominator so that the desired unit seconds will be in the numerator and will be in the answer. So when we get it all set up, it says multiply the time worked by the conversion factors. If we start with 8 hours and we set it up, times 60 minutes over 1 hour. We wanted hours to be in the denominator so it would cancel out. Then the second conversion factor was 60 seconds were in 1 minute, and we needed minutes to cancel out. So that seconds would be the unit in our answer. And then they've got a little balloon here, and it says, before you do the actual math, it's a good idea to make sure that the units cancel. Absolutely is true. Make sure your units cancel so that the numerator and denominator of each conversion factor are equal to each other. If you multiply everything across the numerator, and we've got just ones in the denominator, so you'll get 28. Let me see. This does not look, we've got a little discrepancy here. 8 times 60 times 60. So they left the 8 off right here. It should be 28,800 seconds, and they've got then in scientific notation 2.88 times 10 to the fourth. So they left the 8 out here. But when you multiply everything across the numerator and then divide it by everything multiplied in the denominator, you would get 2.88 times 10 to the fourth, or 28,800. Because these are all unit factors. There's an unlimited number of significant figures, so you don't have to worry about that. You can just write down whatever pops up on your calculator. Okay, and it says the answer has the desired units. Since a second is a small unit of time, you should expect a large number of seconds in 8 hours, and that's true. The answer is exact since the given measurement in each of the conversion factors is exact. Okay, now, second problem. The directions for an experiment ask each student to measure out 1.84 grams of copper wire. The only copper wire available is a spool with a mass of 50 grams. How many students can do the experiment before the copper runs out? So we've got 50 grams total, and each student needs 1.84. From the known mass of copper, use the appropriate conversion factor to calculate the number of students who can do the experiment. What we know is that we've got 50 grams of copper. And the other thing we know is that each student needs 1.84 grams of copper. So what we don't know is how many students. So our conversion factor is one student needs 1.84 grams of copper. So we've got two possible conversion factors, 1.84 grams over one student, or one student over 1.84 grams. And if we're starting with 50 grams, this conversion factor right here would be the one we would want to use, because our final answer wants to give us a number of students, and we need grams of copper to cancel out. So because the desired unit for the answer is students, use the second conversion factor. Multiply the mass of copper by the conversion factor. So if we multiply 50 times 1, which that's going to be 50, and then divide it by 1.84, we'll get 27.174. Now, we can't have part of a student. We can't have 0.174 students, so we're just going to round that off to 27. 27 is the greatest number of students that can do this experiment with the 50 grams of wire that we've got. And this says the unit of the answer is the one desired. You can make an appropriate calculation using the following conversion factor. Multiply the following or the above conversion factor by 50 gives the approximate number of 25, which is close to the calculated value. And it does make sense. Okay, here's an example to convert between metric units, and that's what you're going to do for a little practice today. So it says express 750 decigrams to grams. Refer to table 3.2 if you need to refresh your memory of metric prefixes. And you can look at that in the textbook if you need to, or you can look at back on the notes that are also in the or on Google Classroom. So the desired conversion is decigrams to grams, and it says multiply the given mass by the proper conversion factor. So we have 750 decigrams, and we know that in each gram there are 10 decigrams. So if we start with 750 decigrams, and we know we want to solve for the number of grams, that needs to be our unit for our answer. We're going to multiply this by 1 gram over 10 decigrams. So we're going to use the relationship 1 gram over 10 decigrams. And it says multiply the known mass by that conversion factor. Our units of decigrams cancel out. 750 times 1, and then all that divided by 10 will give us 75 grams. Because the unit gram represents a larger mass than the unit decigram, it makes sense that the number of grams is less. So that is a sensible answer for us. The answer has a correct unit and the correct number of significant figures. And we're going to stop here because we are going to do a separate lesson on density, and then we're going to come back and talk about how to use density as a conversion factor.